So I'm going to go ahead and introduce you to Peter Behroozi.
So I study galaxies. I don't study planets. So what am I doing here? Well, I and a colleague at Space Telescope, Molly Peoples, of course, also studies galaxies. We were thinking about, just one night, crazy things that we could do. And we asked ourselves the question, when and where did all the planets in the universe formed? And perhaps especially because we don't study planets, we thought this might actually be something that we could answer. Okay, so let me give you a brief history of the universe because, of course, we're talking about all the planets in the universe, so where did all the planets come from? Let's start out by talking about what happened first. The universe went boom. It didn't actually look like this, as you might guess. I took some time earlier this morning to figure out what it would have actually looked like in the Big Bang, and it looks like this. So this is Big Bang blue. If your eyes didn't melt right away, then you would see this color. And you would see only this color and it would look very uniform across space because at the very beginning of the universe, the matter density was very even across every part of the universe. And so as the universe grew and expanded and cooled, then tiny density fluctuations in the early universe, if there's a little bit of extra matter here, then it started to pull in matter from its surroundings and then gradually grow and grow. And so after the first period of cooling and expansion, then you started to have the first galaxies forming. And the first galaxies, of course, formed because you had gas coming together. That gas started to cool and form stars. So if I just start this movie playing, you can see the formation of the first galaxies as they start out small and grow from, I guess, gas coming in the surroundings, but then, of course, also mergers with other galaxies that come nearby. And so what you're seeing here with these galaxies is just the distribution of stars. So you're not seeing any colors as you would in reality. Of course, galaxy formation is an ongoing study and what I'm involved with. But you can get the general picture of how stars are forming inside these dense regions where you have a lot of gas that can cool. So once you form the stars in the galaxy, then you can start to form planets around those stars. So stars, of course, don't form in isolation, but they form in a giant disk of gas and dust. So as the star is forming, then of course this disk is evolving and it starts to fragment. And you see initially sort of density waves in the disk of gas around the star, and then you start to see fragmentation, and the fragments then start also clearing out regions in this. There we go. So then you start seeing them clearing out and growing by creating, removing material from their surroundings. Okay. So then you have the basic picture of the universe from its beginning until you start forming planets. So how do we calculate, say, the planet formation rate in the universe as a whole? Well, we start out first by counting how many galaxies are there in the universe. And then we have to do some multiplication. So this is the only equation I'll have in this talk, I promise. And there'll be no symbols even, just pictures. So we start with galaxies in the universe. We count up how many there are. And then we multiply by the star formation rate per galaxy on average. And then we multiply by the number of planets formed per star. So very simple, right? So we just multiply three numbers together. Well, it's a little bit more complicated, so I'll go into a little bit of detail about how we calculate each of these three numbers that we multiply together. So first, oh yes, of course, when you multiply all of them together, then things cancel and you get planets per universe. Great. So first, how do we calculate how many galaxies there are in the universe? So spacecraft, of course, like Hubble are very important, but also telescopes here on the ground. And so what we can do is we can look at galaxies across the entire history of the universe. Of course, because light takes time to travel, the farther away the galaxy is, then by the time the light from it reaches us, then we're seeing the galaxy as it was many billions of years ago. And so the more distant and fainter the galaxy, the older it is. And also you might notice the redder it is, because as the universe expands, the light from the galaxies expands with the universe, and that means the color of the light changes as the universe expands. So the faint and red galaxies in this Hubble image are the galaxies that are farthest away, and then the large and bright and blue galaxies especially are the galaxies that are close by. So we can say at any age in the history of the universe how many galaxies were there. Okay, so then we can ask, what is the star formation rate per galaxy? So there's an easy way to do it and a hard way to do it. So the easy way to do it is to look for young stars and galaxies. And young stars and galaxies are very hot and bright, or at least the stellar populations include very massive stars that are hot and bright and blue. And if you look for a lot of blue light, then you can say, oh, the galaxy is forming a lot of stars. If you don't see that light, then the galaxy is not forming so many. That's the easy way. So the hard way is what my own research is. And my own research is aimed at not only getting what is the star formation rate of the galaxy, but what did that galaxy look like at all times in its history. And so the way that I do that is I build many, many different universes. So using a computer program called the Universe Machine, I build many, many models of the universe with different physical rules for how to form galaxies. And by comparing these mock universes to the real thing, I can ask which physical rules for forming galaxies match up with the real universe. And then, from those physical rules, I can derive things like how did the Milky Way used to look as a function of time. So as you go back earlier and earlier in the history of the universe, then the Milky Way gets smaller and smaller, and its shape also gets more and more irregular and lumpy as you go back earlier and earlier in the history of the universe. In any case, that's how you get star formation or star formation histories for galaxies. And then the last piece is how many planets form per star. And so when we're talking about planets, it's helpful to say what we mean by a planet. So Molly and I, were specifically interested in Earth-like or habitable planets. And Lauren already gave a great introduction to that. I'll just re-summarize by saying, when I think of an Earth planet, it not only includes the Earth, or when I talk about Earth planets, it not only includes the Earth, it includes any planet within the habitable zone. And that means, for my definition here, a planet within a factor of 3 of the size of the Earth in an orbital period, that is the time it takes to orbit around its host star, within a factor of about 3 of 1 Earth year. And so just to give you context, in the solar system we have 3 Earth-like planets. We have Venus, Mars, and Earth that all satisfy those conditions. And the reason that we're including them here is if they had an Earth-like atmosphere with an Earth-like greenhouse effect, then liquid water would be able to survive on the surfaces of those planets. Obviously, not all planets have an Earth-like atmosphere, and so the real number of habitable planets is going to be somewhat smaller than what I'll talk about here. It's also interesting to consider giant planets. And the reason for considering giant planets is that some astrobiologists believe that giant planets are necessary for habitable life to form. For instance, blocking out asteroids, or also potentially establishing stability of the planetary system. So it's also worth thinking about how many systems there are with giant planets in the universe. And it's actually interesting because the number of Earth-like planets formed is not just proportional to the number of giant planets formed. In fact, the more heavy elements there are, so elements heavier than helium, then the more giant planets you form in proportion to Earth-like planets. And so in detail, if you study planets, like with the Kepler Space Telescope, or with Keck or Magellan or other direct imaging, then you find that planet formation rates depend on a lot of things. So the mass of the host star, how many heavy elements there are, the environment, and so on and so forth. And that's maybe why it's hard to imagine calculating the planet formation rate for an entire galaxy, because if you think about having to know these for every single star and add up for, in the Milky Way, there are 100 billion stars, then it seems like an intractable problem. But in fact, having 100 billion stars in our own galaxy makes it an easy problem because a lot of things average out. And so instead of having to go to each star and say, how many planets are you forming, I can just say, this is on average how many planets per star are formed. This is on average how many heavy elements there are sitting around in the Milky Way. And so a lot of the calculation becomes easy. And so I can then just go straight to the results. So what I've done is I've calculated the number of galaxies in the universe, the star formation rate per galaxy, and the average planet formation rate per star. And so then I can get how many Earth-like planets that are formed in the entire universe. And so let me just walk you through what this plot means, because it's complicated. On this axis, I have time. So of course, time starts at the Big Bang here and then proceeds until the present day here. And on this axis, I have the mass of the galaxy that's hosting the planets. And so what that means is the mass of our own galaxy, the Milky Way, is about here. And then as you go higher or lower, then you're talking about different size galaxies. So this is telling you the environment where the planet is forming. This is telling you the time since the Big Bang. And then these different contours here tell you where 50% and where 90% of all the planets, Earth-like planets in the universe, were formed. And this dot with a circle around it here, that's the solar system. And so the reason why Molly and I were talking about this question in the first place is we are interested in knowing, when did our own solar system form relative to all the other solar systems in the universe? And what we found is actually it formed a little bit late compared to most of the rest of the planets, but it formed in a galaxy of about the same size as most of the rest of the other Earth-like planets that were formed. If you look at giant planets, the picture becomes a little bit different, and that's because giant planets require more heavy elements. And if you ask what happens to the heavy elements when you produce them in a supernova in a low mass system, then the gravity of the system is not strong enough to keep the heavy elements around. And so they just disappear and they don't stick around to help you form planets. And so if you're talking about giant planets, then giant planets form in larger galaxies and also at later times when you have enough star formation to build up heavy elements. So what that means is actually the solar system is sitting in right around where most of the rest of the planets and the giant planets in the universe have formed. And so if we look at the history of our own galaxy, the Milky Way, we see something very similar. And so here again, I'm showing you the time since the Big Bang, so Big Bang, present day. Here I'm showing you the total planets formed. And if we look at Earth-like planets here, then again, our solar system was formed late relative to most of the other planets. But if we talk about giant planets, it was formed right in the middle. So if we look at the numbers on the right, we get a very interesting picture. So in our own galaxy, we've formed about order of magnitude 1 billion. So it may be 2 billion, maybe 3 billion, depends on exactly how you count. But if we're talking about the universe as a whole, then we're not just talking about 1 billion planets, we're talking about 10 billion planets. And so that's a lot. And so getting back to the question about, is there life on other planets? Can we find life on other planets? It seems reasonable that even if we can't find life nearby, there should be life out there on other planets, given that there's quite a few of them out there. So I want to say a little bit now about the future. So we talked about the history of planet formation in the universe, but worth saying a few words about what's to come. So if I ask, where is the material, the building blocks for making planets and stars? So this is a graph showing you what is the energy density and matter density currently in the universe today. And so there's a lot of things that we don't know about dark energy, dark matter, and that are the topic of things I study and many others study here. But if you're talking about the fuel for star formation, hydrogen and helium, it's sitting at around 2.2% that's around galaxies and available to form stars. And only 10% of that has turned into stars at the present day. And that means, if you just extrapolate, all that gas is sitting around that'll eventually form stars, then we've only formed 10% of the Earth-like planets so far. And that means in the future, there'll be another 90% left over. And if you ask the question, what does that say for the future of civilizations? That means if we've only formed 10% of the Earth-like planets so far, maybe we've only also formed 10% of the civilization so far. So I just want to leave you with that thought and say thank you